Hi, and thanks for watching another instructional video for CSCI 1300. In this video, we will cover the use of arithmetic expressions in C++ and how to use typecasting as well when dealing with integers and doubles. C++ supports the same four basic arithmetic operations as a calculator: addition, subtraction, multiplication, and division. But it uses different symbols for multiplication and division. You must use the asterisk or star to denote multiplication, and similarly, division is always indicated with a forward slash, not by a division symbol or a fraction bar. Parentheses are used just as in algebra to indicate in which order the sub-expressions should be computed. Just as in regular algebraic notation, multiplication and division have a higher precedence than addition and subtraction. If both arguments of an arithmetic operation are integers, the result will be an integer. If one or both arguments are floating point numbers, the result will be a floating point number. Let's go into some code and talk about this here in a sec, but first I want to talk about some arithmetic expressions that are possible in C++. You will have to use parentheses, but you can use x plus y divided by 2, which will be the same thing as doing x plus y over a division of 2. You can do the same thing here, but parentheses are not required with multiplication because the operators with the same precedence are evaluated left to right. So in this example, multiplication will have a higher precedence than division, and therefore we don't have to specify the order of operations, because the multiplication sign will take precedence over the division. Here, if we want to raise something to a power, we have to use the pow function. There are two parts to the pow. The first is an argument for the base, and the second is an argument for the exponent to raise it to. So you can see here that if we take 1 plus r over 100, we're going to pass that entire expression in the parentheses as the base and raise it to a power of n. Likewise, with the square root function, in order to do the square root of a squared plus b squared, we would type these sqrt parentheses and then pass in what we want to square root. In this example, we're going to type a times a plus b times b, simply because this is simpler than calling the pow function on a and b separately. And also, if we have a series of integers that are declared as variables, such as I, j, and k, and we use a denominator such as 3.0 to divide all of the sum of these I, j, and k variables, we will get a floating point division from the result. And lastly, there are some other mathematical functions that can be used, such as sine, cosine, tan. You can do a base log 10 and an absolute value as well. These come up every now and then, but usually aren't used that often unless you're doing data science or computational intensive mathematical work. Let's jump into some code here and talk about how this translates to VS Code in C++. The first thing that I want to show you is that in order to use mathematical functions, we will have to use and include math.h. We can also use CMath, which is a similar library. This include does a similar job and is just fine to use as much as math.h. So either one of these are applicable. Let's talk about some things that happen with typecasting and specifically how integer division can affect the outcomes of operations in C++ arithmetic. Say we have two variables, integers a and b, and we have some double called c. So this is a floating point number, and a and b are whole numbers. A gets assigned the value of 17, and b gets assigned the value of 5. The next thing to note is that c, being a double storage container, we're going to take the operation of a divided by b and typecast it into c as a double. So when we use the name of the data type that we want to store, the result of this operation into some variable of the same data type, what we're doing here is we're saying whatever comes back from A divided by B, we're going to turn that into a double and then store that here into C. It's also a good thing to note that the highest order operand determines the type of arithmetic precision performed. For instance, double takes precedence over integers because of its number of bits. I'm now going to compile the code, and we're going to run through the output of the program to see what's going on here. When we take A divided by B, what we're doing is we're dividing 17 by 5. So this is a whole number divided by another whole number. And in this example, there is no typecasting involved. So what happens is the integer division rounds down to the nearest whole number. In this example, we should get 3.4. But if we use an integer divided by an integer, then 3.4 gets rounded down to 3 because that is closer than 4. So the result that is displayed here is the rounded down number, which is 3. If we were to take the next line, line 21, which would be to take the numerator, A, and typecast that by giving it the double data type through the typecast operation, and then divide that by an integer, which is still the same value that's stored into B up above, then what we're doing is we're typecasting so that we have a floating point value in the numerator and a whole value in the denominator. In this kind of an example, we get 3.4, so that works. And likewise, we could switch this and typecast the denominator. It works just as well. We get the same result. Also, notice that if we take A divided by B and typecast this expression, the whole expression, what ends up happening is that we get the value of 3.0. It's displayed as 3 here, as well as when we try and print C as well. So what's happening here is that A divided by B, then this integer division is taking precedence over typecasting. So instead of storing 3.4 here, it's storing 3.0 into C. So up above here, C should hold the value of 3.0 because A divided by B takes precedence over the typecasting. So here, when we print C, you can see that it has the value of 3. It's actually 3.0 because of the operation that we did before up above. If we then take that number and we divide it by 2, notice that we get 1.5. So we're getting a floating point value out of it because the numerator is already a double. Even though it's being printed as 3, it is stored as 3.0. So when we divide it by an integer, we will get a double as a result. And here, on line 26, what's happening here is that we're taking the A divided by B argument and then divide by 2. So here, what is happening is that this will take precedence over the typecasting. So A divided by B will give us a rounded down number of 3. Then divided by 2, we get the same answer as above, where we get 1.5. So these will result in the same operation, just in 2 different ways. On line 27 here, what's happening is that we have no typecasting and integer division rounds down. So A divided by B divided by 2, what happens here is that we get 17 divided by 5, which is 3, divided by 2 rounds down to 1. So every time that we divide, we're rounding down. So we divide 17 by 5, we round down to 3. Then we divide by 2 again, we round down to 1. So it keeps rounding down with every division. And lastly, if we do the same thing here and we do it even with a double included in that, notice that 1 divided by 2 should give us the value of 0.5. But because of integer division, we're going to round down to 0. And then, after that, we're going to try and divide by 3 again, and then divide by 4 again. So the whole thing results in an output of 0. That's all for now. Thanks, and happy coding.